Hey everyone, I'm Nick from Coffee Before Arch, and in this episode of From Scratch, we're going to be showing off a simple program that uses CUDA atomics from scratch to calculate a histogram. So we'll go ahead and open up histogram.cu, and we'll go ahead and write down our normal comments. So this program computes a histogram on the GPU using CUDA, right? And then of course by Nick from Coffee Before Arch. So we'll need, of course, our boilerplate stuff. So we'll need a global function. So this will be our kernel, and we can just call it histogram. Okay, and we'll leave it empty for now. And we, of course, need a main function, right? Every program needs a main function. Okay, so the next thing we need to do is how much data do we actually want to or how many data elements do we want to sort into bins? So when we're computing a histogram, what we're doing is we're taking, say, data, elements from 0 to 100, or with random numbers between 0 and 100, 0 and 10, 0 and 26, depends whatever data set you're working with, and we want to sort them by, how is our data kind of arranged? So how many data elements fall between 0 and 10, how many fall between 10 and 20, 20 and 30, 30 and 40, etc. Right, so that's what a histogram will give us. So the first thing we need is, of course, what's our input data set? So here we'll just have number of elements to bin, and we'll say that this will be an int n, and we can go ahead and say this is, say, 1 shifted over 20 times, right? So this will be 2 to the 20 elements, right? So we'll go ahead and say 2 to the 20 default, right? So this will take about 4 megabytes, right? Because 2 to the 20 is equal to 1 megabyte, right? But there's 4 bytes per int, so it'll be 4 megabytes. Okay, and then we'll go ahead and calculate that. So we'll go ahead and say size t bytes is equal to n times size of an int. So this is how much space we need to allocate for our input array. So then we need to allocate space for the bins as well, right? So if we want to sort into, say, 10 bins or 5 bins, etc., we need a place to store the bins, right, on the CPU and on the GPU. So in this case, we'll go ahead and have so select the number of bins, and we'll say int in bins is equal to, we can give it a nice even number like 10. The other thing we need to do is we need the size of this, right? So size t, and we can call this, say, bytes bins is equal to in bins times size of an int, right? So this is how much space we need for our array that represents our bins. So the next thing we need to do is we need to go ahead and allocate space, right? So we need to go ahead and do this allocation for both our input array of 2 to the 20 elements and our bins, which is just 10 elements or 10 integers. Right, so we'll go ahead and allocate memory, and we'll need 2 pointers, right? And we'll call one of these the input, and we'll call another one of these just bins, right? And so we're going to be binning the input. So here we'll use CUDA malloc manage, so we don't have to do explicit memory copies, right? And we'll go ahead and do and take the address of input, and this will need bytes of memory. So bytes corresponds to in times size of an int. And then, of course, for the other one, for our bins, we'll go ahead and fill bins, and it'll point to a space of memory that allocated for 10 elements, or in or bytes bins worth of elements. Right, so now we've allocated memory. Missed an S. There we go. Okay, so the next thing we need to do is we need to go ahead and allocate our data, or not allocate our data, we need to initialize our data, right? So here we'll have, we'll have a simple function, so we can just say initialize our input array with random numbers from 0 to 99, right? So we'll need to include something here, which is cstdlib, right? cstdlib, right? And this is how we get access to rand. If we want to better random numbers, we'd actually include random. But this is fine. We really just care about functional correctness here. And most of the time, if we're actually computing a histogram on something, we're probably not going to be computing a histogram on just random data, right? We'll have some kind of input that we want to compute a histogram for. Okay, so with this, right, so we'll have a void function, init array, and then we'll pass in a pointer to an array, and then the number of elements in, right? And that'll be an integer as well. So here we'll do for int I is equal to 0, I is less than n, oops, I plus plus. We'll go ahead and set a of I equal to rand mod 100, right? So this will give us random numbers between 0 and 99, right? And we can go ahead and go down here, and we can say init our input array, right? So we'll just call init array on input, right? And of course it's in elements. Now the other thing we need to do is we need to go ahead and initialize our bins, right? So we can either do this on the GPU or we can do it on the CPU. It's easiest to just do this on the CPU because there's not really that many elements here, right? So if we want this to, have any kind of performance, there's no point in having to transfer the memory all the way over to the GPU just to initialize these 10 elements to 0. So what we can go ahead and do is set our bins equal to 0, right? So we'll just do a simple for loop, int I is equal to 0, I is less than in bins I plus plus. And then this will simplify our kernel as well because we don't need to, selectively zero out our bins. Okay, so let's go ahead and set this to 0. So this will be bins of I is equal to 0. All right. So now we're ready to kind of get to the meat of this application, which is we'll go ahead and select our blocks in our grids, and then we'll go ahead and launch our kernel, and we'll have to write our kernel. So here we'll say set the dimensions of our CTA and grid. So for this, right, we'll say int thread, so this is the number of threads per thread block. We'll set this equal to 512. It doesn't really matter here because we're not really reusing anything between these different threads, so we don't need to worry about. So we can pack really as many threads we want into each thread block. We don't have to worry about limitations like shared memory because we're not using shared memory right now. So 512 is a decent number. Generally, you pick something between 128 and 1024. Right? So in this case, right, so we'll just pick 512. And then if we want every single thread to compute an element, right, we'll say int blocks is equal to, and then we'll do this padding technique where we'll do n plus threads minus 1 divided by threads, right? So this makes sure that we launch as many blocks as we need to cover all the threads, but we might have to add more threads than we have elements here. So we'll have to take care of that in the kernel itself. Okay, so then after this, we can go ahead and call our kernel, right, with blocks and then threads, right, and because we're using CUDA unified memory, we're not doing explicit memory copies, which means we need to go ahead and make sure we synchronize after the kernel launch because kernel launches are asynchronous. So we'll do CUDA device synchronize, right? And then we'll add a return 0 at the end of the program. All right, so now we've got a program where we're at least calling a kernel, we're allocating memory, we're initializing everything. So we actually have to start computing a histogram here. So what do we need to input to our histogram? Well, we need to go ahead and input our pointers, right? So our input and our bins. We need the number of elements that we're going to be binning. We need the number of bins that are going into. And one thing we can also do on the host side or on the CPU side is calculate, what I should divide the input element by in order to find what bin it belongs to, right? So if we say have numbers between 0 and 9, right, inclusive, so that means we have 10 total elements, and let's say we have 2 bins. Well, 0 through 4 should go in one bin, and then 5 through 9 should go in another bin, right? So the easiest way to calculate which bin it should go into is whatever the input data element is, divided by the number of bins, right? 5, so 5 elements in the first bin, 5 elements in the second bin. So all I would need to do is divide whatever the input element is by 5, right? So 0 through 4 divided by 5 is an integer, right? So it would get rounded down, right? So that'd be equal to 0, and then 5 through 9 would get rounded down to 1, right? And that corresponds to the index inside of bins. But we need to make sure that we have some padding in there. So what if we have, say, 11 different elements, so numbers between 0 and 10, but we still have 2 bins? Well, if we did 11 divided by 2, right, that would end up giving us 5.5, but it's an integer, so that would get rounded down to 5. Now, what happens when we get to the element that is the number 10, right? Or if we have a random number that is equal to 10? Well, 10 divided by 5, which is what we calculated as our divisor in order to find the bin, that would give us 2, right? And 2 is an invalid index. So we need to make sure that we do some padding here, right? So the way we do that, right, we'll go ahead and put this here by our init array. So we can say, set the divisor for finding the corresponding bin for an input, right? And so it's just like this blocks calculation down here, where it's n plus threads minus 1 over threads, except this time it's going to be whatever the input distribution is, right? So we'll just call this div, right? Right, so div will be equal to whatever our input is. So we've got random numbers between 0 and 99 inclusive, right? So that's 100 different numbers. So we need to make sure we've got space for 100 plus the number of bins, right? So in this case, it'll be in bins minus 1 divided by in bins, right? So this makes sure in the simple case, so if we go back to that example where we have 11 different possible input numbers and only 2 bins, so this makes sure that elements 0 through 5 go in the first bin, and then in the second bin it'll be elements 6 through 11, right? So even 11, though 11's not ever going to happen, right, because that's not in our input data, we had to pad kind of the first half. So we have uneven bins now, and this will happen whenever you have whenever your number of bins does not equally divide your data. Okay, or does not equally divide whatever the maximum element in your input data is. Okay. So now we've got all these inputs set up, so we can go ahead and pass them into our kernel. So we'll pass in our input data. We'll pass in our bins array, and we'll go ahead and pass in and in bins, and then we'll pass in div so we don't have to calculate that every time on the GPU. Okay, so now we need to go ahead and we'll split this. We'll go to the top of the program, and then we'll go ahead and write in these inputs here, right? So the int pointer for input, an int pointer for bins, an int for in, an int for in bins, and of course an int for div, right? That's our divider to figure out what the corresponding bin is for this element. So the first thing we need to do is we need to differentiate the threads. So we need to figure out which thread should do what. So the way we've set up this problem, every single thread is going to bin one element, right? So we'll have int row, so we'll say calculate the global thread, thread ID, right? So this will just be int tid is equal to block idx.x times block dim.x plus thread idx.x, right? So this block idx.x times block dim.x, this just says, which block do I belong to, right? And what's that offset in threads? We have blocks that are size 512. If I'm the first block, the starting thread for that block is 512, right? So it'll be 1 times 512, right? And then to figure out which thread I am within that block, the offset is thread idx.x. So within each block, we have threads 0 through 511, right? So it'll be 512, and if you're the first thread in that block, it'll be plus 0. Second thread plus 1. Third thread plus 2, etc., right? Because it's 0 indexed. The next thing we need to do is we need to make sure that we actually belong to the problem, or rather that we should be doing work here. So we'll have a boundary check. So we'll just make sure if tid is less than n, right? Because we have n elements, and every single thread will compute, 0 through n minus 1, right? Or rather, one thread will be mapped to an element from 0 to n minus 1, so it has to be, the thread ID has to be less than n, right? And if it's less than n, what do we need to do? Well, we need to figure out the bin, right? So this will just be equal to whatever the input data is for this TID. So again, every thread maps to one input element divided by div, right? So this is how, some number divided by 5 would go into the first bin. In that simple example, it'll be some number divided by this div will go into an arbitrary bin that we've calculated on the host side code. Okay, right? And then the next thing we need to do is we need to just store that information, right? So bins, and we'll index this with bin plus equals 1, right? So for each element, we just figure out where it should belong to. Now there's a problem in this code, right? And the problem in this code is that right here, this bins of bin, right? So this leads to a race condition. And the reason why is because every single thread on the GPU is accessing the same array, which means that they're all trying to write to this array at similar times. So unlike in CPUs that have cache coherence, so there only one thing will be able to write at the same time, GPUs don't have cache coherence in the L1 cache, right? So what can end up happening is that a thread will go ahead and or a group of threads will try to write to bins while another group of threads is trying to write to bins, so we won't actually see all the updates, right? And because we don't see all the updates, this means that we're probably going to lose some elements. So if both the threads read 0, right, as far as what a bin is, then they both add 1 to 0, they both update it to 1, and then they both send it down to the memory system, or through the memory system, and we lose one of them, right? So what should have happened is if both threads try to increment this bin by 1, we would expect 2, but we can end up seeing 1, right? So, we'll show this, how this is actually a problem by, after here, what we'll go ahead and do is, let's actually include a couple things. So we'll include std or IOStream rather, right? And then we'll go ahead and using namespace standard just for some convenience, right? And then afterwards, we'll have some int temp is equal to 0, right? And we'll go ahead and do for int I is equal to 0, I is less than n bins I plus plus, and then we'll do temp plus equals bins of I, right? So all we're doing is accumulating the total number of elements that have been binned. And what we would expect is that this would be equal to, say, 2 to the 20, right? And we can actually reduce this problem down, just because 2 to the 20 is a rather big number. We can reduce this down to, say, 2 to the 10, right? So 1024 elements. Okay, so then back down here, what we'll show off is why we care about this race condition is we'll just print out the number of elements that actually got binned. So we'll print out temp end line, and that's actually going to do it for us, right? So let's go ahead and just compile this, make sure we didn't make any silly mistakes. Histogram -o histogram, and we can go ahead and run this. Okay, so we expected 1024 elements would get binned. We actually only got 10 total elements, right? So we did a sum of all the counts and all the bins, right? And so when we'd expect 1024 elements to get sorted into 1024 or into 10 bins, it doesn't matter that there's 10 bins, all 1024 elements should be in those bins. But in this case, right, we only see 10, right? So we're missing data here. So that comes from this race condition right here. So how do we get rid of this race condition? How do we make sure that everybody's increments will get counted, right? And for this, we can go ahead and use atomics, right? So atomics will make sure that everybody, all these transactions will complete, and they'll complete in some global total order, but they won't complete, say, concurrently, right? So you won't have competing writes overwriting each other. They'll all get eventually pushed into one straight line that will be visible to everyone, right? So to use this, we'll use atomic add, right? And how do we use atomic add? Well, we have to pass in a memory location, right? And that memory location will be, we'll just take the address of bins of bin, right? And we want to add 1 to it, right? So this is how we kind of fix this problem, right? And then we can go ahead and recompile this, right? And so last time the problem was, when we just ran the code, only 10 elements actually got binned. Now all we've done is change, a normal add to an atomic add, right? And we can go ahead and run it again, and you see that all 1024 elements, got binned. Okay, so we can even scale this up more. So we can scale this up to, let's go ahead and get rid of this. This leads to a race condition because we fixed that now. Oops. And let's scale this back up to our originally sized 2 to the 20 elements. And we can go ahead and get rid of this print now, right? This was just for kind of, actually we get rid of these two, right? So now that we've kind of confirmed that we're doing the right thing now, let's go ahead and compile this. And we'll run it again, right? So now, we've got a program using atomic ints. So this is atomic in main memory, right? So we're not using atomics with shared memory right now. In the next video, we'll show how to do that, right? So let's kind of go over everything again. So we want to compute a histogram, and so we have 2 to the 20 elements that we want to bin, right? How many bins do we want? We want in bins, right? And so we go ahead and set the size of these two things, and then we allocate these, right, using CUDA unified memory. Then we initialize our input array with random numbers between 0 and 100, or 0 and 99 inclusive, right? So 100 different numbers. Then we set the divisor for finding the corresponding bin for an input, right? So this will just be 100 divided by in bins. But if these numbers don't divide equally, so if 100 doesn't divide equally by in bins, we need to make sure that we add some padding here. So just like we do with blocks down here. Then we go ahead and set our input bins to 0 because we don't, when we allocate memory, there could be stale values in there that we don't necessarily want, right? So we'll just set all these values to 0. We're going to use 512 threads per thread block. This is a number that you could play around with and see if the performance changes. And something like this, we're not really packing much work into each thread, so it's probably not going to make a huge difference. Then we have our blocks, right? So our blocks will just be in divided by number of threads. And then if we don't have a number in that's evenly divisible by 512, we'll have to go ahead and pad it, right? And that's what this threads minus 1 is for. Then we actually launch our kernel. So we pass in our input arrays of input and bins, the number of input elements, the number of bins, and then this divisor in order to figure out which bin each element should belong to. We synchronize just because kernel launches are asynchronous, so we need to make sure that the kernel completes before the program continues. Then inside of our histogram kernel itself, we calculate a global thread ID so that every thread knows who it is in the system. We make sure that the thread corresponds to a valid element in our input array, right? So if we have in elements, we should have in threads, right? And because they're 0 index, we can use TID as less than in. Because our elements will be from 0 to n minus 1 indices. Right, and then we calculate which bin this element belongs to. So that will just be whatever this thread, the corresponding input element for this thread, so input of TID. And then we divide it by that divisor that we talked about. And then we do an atomic add just to make sure that every single one of these adds completes, right, and doesn't overwrite anyone else's value. We showed that if we just did bins of bin plus equals 1, we showed that when we did that, we got a race condition and we didn't actually see all the updates complete, right? And so to fix that, all we did was use atomic add instead, right? So this makes sure that there's some global total order of these updates, right? And they don't conflict with each other. Okay, so that's going to go ahead and do it for this time. Next time we'll show off some cooler things we can do with atomics in terms of using atomics in shared memory instead, and how we can, kind of improve on this histogram kernel by not always having to do atomics all the way out with global memory. But like I said, that's going to do it for this time. As always, feel free to check out any of my stuff at github.com/coffeebeforearch. So we've got a whole bunch of repositories here. We got this from scratch series where I post all this code, as well as the other CUDA programming series, right? Where most of the where most of these examples come from originally, right? So we've got stuff on vector addition, matrix multiplication, CUDA library, sum reduction, convolution, right? And here's a histogram example. So we've got this version that we went over today, right, which is kind of the simple version with some more comments in it. And then we've got a version that uses shared memory, right? So we've got shared memory in here. Like I said, that's going to do it for today. As always, I'm Nick, and I hope you have a nice day.